Some of the important things about precision agriculture for Hawaiians is, for farmers, obviously they're better able to address their crops' needs, and so they can maximize their yield. But also it reduces the cost and waste that they might apply with fertilizers. So if their crops don't really need the fertilizers, they don't have to spend the money to use that fertilizer. And then as an environmental impact, if the crop doesn't need the nutrients from the fertilizer, those fertilizers will run off into the groundwater and the surface water, which can have serious health effects and environmental impacts. And the last one is the efficiency. So with a drone, we were able to cover about 6 acres and get data, high resolution data of those 6 acres in one flight, which we just did on an app, and that flight lasted about 15 to 20 minutes. So we're saving the farmers time also by using these drones. So this is Iceman. It's our drone. It comes with some cool features. So the first one that most drones have is this RGB camera. This will just give you the normal image that you think of when you take a picture. And then it also came with a near infrared camera. This gave us data about NDVI, which we'll describe later, but it's not sensitive to temperature. So we also made some custom modifications, and we built another platform and attached a far infrared camera, which gives us information about thermal data. And so when we fly the drone once, we actually get 3 sets of data, which is very useful, and as we mentioned, it's efficient use of our resources. And that's some thermal range. And so what is NDVI? NDVI has been used to identify the crop health, essentially from these images. It's a ratio that involves the reflected red light and the reflected infrared light. And so basically the idea to know is a really healthy dark green plant is going to have an NDVI close to 1, and dirt, water, a really unhealthy dead plant maybe will have an NDVI close to 0. And so we were looking at a cornfield, and so for that we're looking about 0.4 to 0.6 is a healthy crop. So the goal of our project was to use NDVI to understand the health of the crops that we looked at and identify any variations, and then also understand the factors that go into the variations of crop health. So this is our research site. It was at a corn farm near Hilo. We chose this site, as we'll define. We looked at a subsection of his farm, one with the north field and the south field divided by a road. And some interesting things about the field is that there's a slope going from the south to north. So this, as we go north down the field, the elevation decreases. And so we could see variations in the crop height along with those elevations. As you can see here, as you can tell, the sloping is down, and the crop height actually, and the crop density actually varies with that elevation. And there was also a problem that we were told about with feral pigs. So that means they would be running through the crop field, eating corn, also just knocking stuff down, ripping up the soil, and that will also lead to variations in the crop health. So the first thing we did was we flew a drone path over the field of interest, and we got NDVI images. As a reminder, we're looking from 0.6 to about 0.4 for variations in crop health, 0.6 being the healthier crops and then 0.4 being the unhealthy crops. And from this, we identified 13 points that would be interesting to look at. And at the same time, we went to these sites and collected various data about the soil, the crop height, the temperature, the water moisture content. And these were all part of the key crop health variables that we identified. So I'll talk about some of the metrics that we use for crop health. Obviously, NDVI, we want to support it to test if the drones actually that get NDVI works. We should look at NDVI as a factor of crop health, but then also the corn height. So if there's taller corn, that means it's obviously been able to grow well, and it will have pretty green leaves. And then the length ratio and this is corn length ratio. So we're talking about the actual corn, the length of that to the length of the husk, including the leaves. So if that ratio is closer to 1, meaning the corn is filling up the entire leaves, that means it's a healthier corn. It's got time to grow and mature into the leaf that it was grown with. The other things that we looked at were nitrogen and phosphorus, which are two very important nutrients in the soil, and the pH of the soil. This is important because corn has an optimal growing range from 5.6 to 7.3 pH. And if you need a refresher, pHs closer to 1 are more acidic, and then pHs closer to 14 are more basic, and around 7 are neutral. And it's important to see the pH of the soil because tropical soils, like in Hawaii, tend to have more acidic soils. And so if the pH is lower than 4.0, corn survival is unlikely. So we need to check if there's a danger of that. And then the pH of the soil also determines the availability of nutrients such as phosphorus. We also looked at soil moisture, which is the water content of the soil. So if there's not enough moisture, there's not enough water for the crop to get. And then temperature, if the temperature is too high, there might be some stresses on the plant.
All right, thanks, David. So for our data analysis, we were essentially trying to link NDVI to the parameters that David mentioned and see if we could pinpoint what was actually causing disparities in crop health on the field. The first two that I think of are the nutrients, nitrogen and phosphorus. Corn requires a lot of nitrogen and phosphorus in order to grow. So it really needs nutrient-rich soil. So we were able to run a bunch of tests on soil samples across all the locations that we looked at. And we found on average that nitrogen in the form of nitrate had a concentration of 22 milligrams per kilogram, which is in the high range. This is a range given by an associate of the UC or California agricultural programs. So right away we can basically rule out that nitrogen is not causing any problems in the field. Next, we looked at phosphorus, and we found some much more variable results. In the northern field, samples were depleted to sufficient, and then in the southern field, they were adequate to sufficient. So we'd obviously need to do some more work here to figure out exactly what could be causing this. And then also, we need to look into pH, since phosphorus solubility is greatly affected by that. So if we had more time, this is an area that we would continue to explore. So before we get to talking about the pH, I'd first like to mention the corn height and how it compares with NDVI. So the size of the circles on the left indicate the bigger the circle, the higher the height in inches. And so you can see there's a pretty wide range of values from 44 to 82. And the southern field seems to be pretty consistent in higher values. So we took all these data points and plotted them in order to find a potential correlation. And it turns out that corn height is actually pretty strongly positively correlated with NDVI, correlation of 0.7, given the average values that we found. So why is this? NDVI works and increases by the amount of infrared light that the leaves reflect. So the taller plant you have, the more leaves you'd expect. So therefore, you have a higher green density and more infrared light reflected. So it makes sense, and then the work that we did actually confirmed it. So that's pretty cool. Next, we're going to look at the pH and compare it to the NDVI. pHs were rather acidic across the board here, but that's a characteristic of Hawaiian crop fields, so we were expecting that. As you can see, it ranges from 4.65 to 6.14. So given that range, we'd hope to be able to find some relationship between the pH and the NDVI values. When we did the plot, we actually found a lot of variability between pH and the NDVI. It's negatively correlated by 0.18 from what we found. And the reason for this might be that there's more going on than just this relationship. You have to take into account the solubility of phosphorus, which is optimal around 4.5 and then at 8. So your sweet spot for corn, which is 5.6 to 7.3, actually is not a good range for phosphorus solubility. And the plant can really only access that if it is soluble. So that could be part of it. So based on this, we think that there might be more going on, and it could be a relationship of variables interlinked. So it's definitely something that we'd like to continue to look at. Just to summarize what you guys have heard so far, in the crop field, we found that nitrogen is not a limiting factor. It's pretty powerful though, because if you think a field needs more fertilizer because some parts are struggling, and you just went ahead and dumped a lot of nitrate on there, you'd actually have no impact because nitrogen's in high excess in the field already. Next, we saw the strong positive correlation between the NDVI and height, and we'd like to continue to look at the pH and NDVI relationship and the phosphorus concentrations. So at this point, Megan's gonna take over and talk to us more about the drone.
Yeah, so like Josh mentioned, we have some data that we can gather just by sampling in the field and doing some chemistry on our soil samples. But we also have this nice fancy drone, so we wanted to use that. So a valuable thing that we can get from the near-infrared camera is NDVI. But first I want to mention the RGB photos that we took. So this is an elevation map that we created using the RGB photos in a software related to the drone. Just as a reminder, this is where our field was located. So as you can see, the north and the south field, oh, it doesn't work on the screen. Okay, the north and the south field are here. This is north and south. And then you can see, what? What are you saying? You can see that the green is lower elevation, red is higher. So as these contour lines go up, these are each 5 meters higher in elevation. So we can see there's a small hump in the middle, and then it gets lower in the north and the south. So we can look at the field NDVI. So this is all the transparent parts are non-vegetation. So we correlated, or we compared with the RGB image to determine where the soil and the vegetation was. We found the threshold of about 0.38 NDVI gives us a good idea of where the corn and the natural vegetation are compared to the soil. So our threshold, or our range here is from 0.38 to 0.68, and we can see a denser green area in the southern field versus the northern field, more sparsely green, which is higher NDVI. So then looking at the elevation and,
so just to add some more quantitative analysis of the northern field and southern field. We did some analysis of the pixel or NDVI values from the two fields. So you can see from the histogram here, the x-axis is the NDVI value, and the y-axis is how many pixels or how much of the area coverage has that NDVI value. So we can see that the south field, which has the green curve, and then the north field has a red curve. So the north field has a wider spread just because we have more area ranging from bare soil to some green vegetation or corns. But then in the south field, which is doing slightly better, we have a narrow range because the plants were doing better, and the NDVI value were also better. If we look at the average, it has a 0.470. So you might be wondering if that difference is large enough to make any conclusion about that. But I think it's really useful if we can also look at the histogram, or how much of the distribution from the two fields are. So if we look at the area that has an NDVI value of greater than or equal to 0.38, which we define as soil, we can see that there's much more area in the south field that has that NDVI value greater than that threshold value of 90 93% versus 77%. So from this data, we can easily see that we can fly the drone once and then analyze the statistic for the whole field.
Yeah. So then when we're looking at NDVI as compared to elevation, we can see sort of a confirmation of this more green in the south field versus green in the northern field. So generally, we can sort of hypothesize that as elevation changes more, the corn might have a harder time growing due to water and fertilizer runoff. And we can observe that just as broad trends over this field. So when there's more elevation contour lines closer together, slope is changing more, which happens in the farther north part and the southern part of the field. So where it's less flat, we see a lower NDVI. You can see in the southern field, as it's flatter, the corn seems to be doing better than where it's farther south and the elevation is changing more.
So in addition to the regular RGB or image that you would get and the near infrared, which give you NDVI value, we also have the thermal camera on the back of the drone, which we add on to later. So this camera can give the measurement of temperature. So why is temperature important for the field? So if the temperature is high for a long time, then that could give the plant some heat stress, and that could make like a bad effect for the crop health. So this is the data from January 24th, where we fly the drones 3 times on the exact same path. The first one is from around noon, the second one is from 2 p.m. and the third one is like from 3:20, which is about 1 hour and a half to 2 hours apart from each other. So the scale here is purple meaning cooler, and then yellow meaning hotter. So the temperature ranges from 16 degrees Celsius or about 80 degrees Fahrenheit to 29 degrees Celsius to 84 degrees, about 84 degrees Fahrenheit. So we can see that the temperature of the crop changes from the cooler side, and then at about 2 p.m. in the afternoon, it gets warmer, and then after that, in late afternoon, it cools out. As a analysis for one specific region, so we choose the area over there, which is in the north field, where the plants were doing a little bit worse compared to the south field. This area has a little bit of some destruction or bare soil. So I think this area will give a good statistic from range of the temperature. So if you see in the plot here, the x-axis is the time, and the y-axis is the temperature in degrees Celsius, and the green line is the minimum temperature from that image. The blue line is the average temperature, and the red line is the maximum temperature within that area. So we can see the trend in general that the temperature increased and then decreased later in the afternoon. So given that the weather condition on that day was partly cloudy, we would expect that if it were a sunny day, we would see more extreme change, and we could easily use the thermal camera to identify the specific locations where plants might experience some heat stress. Also, the optimal range of the temperature for corn to grow is about 18 degrees Celsius to 33 degrees Celsius. So on that specific day, the plant was not going out of the optimal range, and it should be good for the corn growth. In addition, to emphasize on the importance of temperature, the temperature, if there's an area that has a lot of bare soil or high temperature, that could make a feedback loop for that negatively affect the plant health, because if you have a lot of bare soil, the temperature rises, and then if the temperature is too high, then the plant is doing worse, and then that could be less leaf coverage, which then again leads to more bare earth. So in conclusion of our project on precision agriculture, we can use drones or UAVs um, to efficiently get a lot of data compared to the conventional method of using satellites. We can fly in whatever path we want and get higher resolution image in short time. Despite some challenges with different weather conditions on different days and some complex image processing, we can still gather lots of information that could help the farmers. Farmers can easily identify the specific locations that plants may need more sample and care. And then farmers can go into that location, do some more soil chemistry, and then determine whether some more fertilizers or whatever types of care they need to apply to some sites. And now we are moving on to the second project of our trip.
Thank you, James. So, yeah, let's move on to the second project, low-cost air particle sensors. So, in this project, we aim to build low-cost particulate matter sensors network to observe and monitor the air quality on the big island of Hawaii. Before we go further to the sensor stuff, let's get a bit of the background why we care so much about the air and why we're doing this research. So last year, Trex, as Megan has already mentioned, they did a project on sulfur dioxide, and this year we're interested in particulate matter 2.5, which is like the particle or droplet that has size or diameter smaller than 2.5 microns, or like about 30 times smaller than your hair. So this case, because these particles or droplets are so tiny, they can go through your respiratory system, go to your cardiovascular, go to your blood, and create so many diseases: asthma, heart attacks, lung disease, premature death, and many more. And if you don't really know, it's responsible for air pollution in general, responsible for 7 million deaths per year, which is even higher than car accidents. So this is why we're interested in air pollution. And where are these pollutants come from? Where the PM 2.5 form? It can be ranging from agriculture, industry, transportation, or combustion in general. But here in Hawaii, we have volcanoes, which is a uncommon source of sulfur dioxide and particulate matters that you cannot really find in other places in the US. There, as I mentioned, there's particles and pollutants generated from the volcano. And the reason why we want to focus on these two particles, there's some chemistry behind the reasons. So the volcano emits some gases. We call those gases volcanic emissions or VOC. And most of the time they came from in the form of sulfur dioxide directly from the volcano. And as it goes through, hours go by and react with the sunlight, it creates particulate matter, which is as I already mentioned, is super harmful and dangerous to our health. And yeah, it's fresh rock directly from the volcano and change over time to edges rock. And another bit before we go to the sensor part, I would like to introduce the idea about the winds that affect Hawaii. So we have two types of winds here: trade winds from the northeast and Kona wind from the southwest. And the winds generally wrap around the island, going to the south, and then turn up here near the south point. And you can see the stars, 5 stars around the island here. These are the Department of Health air quality monitoring stations that existing at the moment. You can see they're not that many. So, and at these stations, they have a sensor called BAM, Beta Attenuation Monitor. This a fancy sensor that costs about more than $12,000 US, and they can give you really precise and data of gases in the atmosphere on the air. But as we know, it's pretty expensive. You cannot have these kind of thing, have a big network of these things. So it's time to introduce our sensors. So this is one of our sensor. So actually like we call this guy a sensor box, and it has a name, Kadaba. We name this box. So it's generally like a box that contains sensors. You can see if you open it up, you can see different like sensor. You can see the blue box there. It's actually a particulate matter sensor that has a fan that draws some wind in it, and inside the sensor there's a laser beam. And once the air go through the laser beam, it scatters the laser, and the sensor could tell you how many particles or the size of the particles that was in the air. And beside the particulate matter sensor, we also have another sensor over there. It's like a tiny hole there. It's a liquid humidity and temperature sensor. This can tell you both temperature, liquid humidity inside the box and outside the box. And so we have the sensors, and other than that, we also have a circuit board that kind of like connect everything all together, and also like save our data into a micro SD card so we can read the data after that. And we also have a display. You can see here showing the current or like real-time particulate matter level, and also a battery like behind the circuit that's kind of like can be recharged by solar. So it's like a solar panel here. This is pretty nice. And now we got all the sensors built up.
So actually we built our sensor back in MIT 1 week before we came to Hawaii, and we managed to build around 14 sensors in total, and we bring it to Hawaii to put it in action. But before that, we first need to calibrate all the sensors first. We did that by we go to the Pahala air quality station, and we put the sensor there and we calibrate it. And after we calibrate all the sensor, we put it in action. First we do a plume chasing. We put the sensor on top of the car, and we drive from National Park, Kilauea National Park, all the way to Kona. And while we drive to Kona, we also put some sensors along the way, creating a sensors network, which will be talked about later on. And here is a picture of our group putting sensors on top of the air quality station in Pahala. And basically, we mount our 14 sensors on the wood rack, and we left it up there around 24 to 48 hours. And then we take the data out and do some analysis to see how it works. And here's the result. You can see that we have a data of many sensors that we name up, and all of them seems to correlate with each other greatly, as you can see. And all the correlation is greater than 0.9, which is really. We also do some correlation with the data from Pahala Air Quality Station. Even though the correlation is not as high as this one, because the air quality station measure the PM in an hourly basis, but our sensor measure in every second. However, our sensor can capture the trend that the air monitoring station can capture. When the station can measure a high concentration of PM, our sensor also did, and vice versa. And here is our plume chasing. So we put a sensor on top of the car. It's a hard work up there, and we also put some sulfur dioxide sensor beside our PM sensor just to get more data about it. And we drive from National Park to Kona and back on the 24th of January. From the National Park to Kona, we took around 2.5 hours, and on the way back, we took around 4 hours. So here's the result. The white dot here says that the concentration of the particulate matter around National Park is around 0 to 5 microgram per cubic meter. But around Kona, we got a concentration of about 10 to 15 microgram per cubic meter. And just a background, EPA says that the threshold of the concentration of PM that could be harmful to human health is around 35. So we are doing fine on that day. It's not that bad yet. And and the trip from National Park to Kona is in the morning. We left around 10 and arrived there around 12:40. And here's the general wind direction on that day. So the wind, as Ju mentioned, as Adam mentioned, wind come from the wind come from the northeast and wrap around Ocean View and go back up to Kona, bringing the sulfur dioxide back to Kona, and it formed the particulate matter around that. And here's the way back to National Park. You can see the same train over here, and we left Kona around 12:45, and we reached National Park around 5 p.m. So this is in the afternoon, but we can still see the same train. And here's the comparison between the way forward and the way back. So to get a deeper understanding of how the particulate matter form, we also do a measurement of other factors that we believe will affect the formation of particulate matter. And these factors are such as relative humidity, temperature, and sulfur dioxide, and also just the direction of wind in general. And start with the relative humidity. As we all know that around National Park or hillside, it tends to rain a lot. And here does not rain as much. So obviously on that side, the relative humidity tends to be much higher, around 70 to 80%. But here on this side, it's only around 40 to 50%. This is also consistent with the measurement of the PM that we capture, because when there's a high relative humidity, there's a water droplet on the air, and those water droplets can capture the sulfur dioxide and bring it to the ground, and doesn't let it to form a particulate matter. But in Kona side, there is not much water droplet, so particulate matter tends to form in a higher concentration. And here's the temperature, and obviously in Kona side it tends to be warmer or hotter than National Park or hillside. And this also affects the formation of particulate matter, because in a higher temperature, the reaction that form particulate matter tends to go faster, resulting in a higher concentration also. And lastly, we measure the sulfur dioxide, and on this particular day, the concentration of sulfur dioxide is quite low. We also check with the data from the air quality station of the Department of Health, and the data is consistent with each other. And now we will move on to our last thing we do, which is a network sensor, which we are going on.
So as Chung mentioned, we placed a network of sensors along the path of the volcanic plume from Pahala to Kona, and this created a small-scale network of sensors. So left one here on top of the Pahala air quality station. Then this one was at the Kau police station. This was at lava flow by Ocean View. And here we have school. And this was another police station. This was a Thai restaurant, the Bangkok House. And this is the Kona fire station. So then we left them out for about a day, and here's the average PM 2.5 from sensors from January 23rd at 6 p.m. to the 24th at 11 a.m. So as we can see here at the ocean view sensor, we have a jump where to the east of it we have considerably smaller values, and at ocean view to the west we get larger values. This is what we expect to see since it takes time for UV light to turn sulfur dioxide into particulate matter. So as the plume travels, it hits a certain point where we start seeing more particulate matter. We also took the hourly averages, and here they are. So again, we are expecting to see increases during the day in general, since there's more UV light, and decreases during the night. Obviously, there will be some exceptions, since that's not the only factor. The plume could have different thicknesses. There also may be some automobile influence. But watching this, it seemed that there was some connection in the increase and decrease of the ocean view sensor and the CODA sensor. So we decided to compare those two, and since ocean view is generally the turning point of the wind and where the plume turns, we only looked at the times when the wind was going in the direction from ocean view to CONA, which gets us this. So here we see the PM 2.5 from the ocean view sensor in blue and the CONA sensor in red from 4 a.m. on the 24th to 11 a.m. And as you can see, there are two periods when the wind was blowing in the desired direction. And the first one is early morning before sunrise, and we see they're both following the same path, going down. Again, this is what we expect to see because there's less UV light. And then later in the morning, after the sun's risen, we see an increase in both of them, and they're generally following the same path. And what we can see here is that the ocean view sensor peaks somewhat before the CODA sensor. And now, obviously, this is just the first step. There's more research to be done with more sensors for more time. But what this shows us is that there's a potential in a predictive capability where if we do learn the right patterns, we'll be able to predict where particulate matter will be in one location based on sensors in another location beforehand. So in conclusion, we have verified that these low-cost sensors do work and can detect trends in particulate matter across the island. And while there will be more research that needs to be done to get to the point where we need to be, there will be value in building a network of many of these low-cost sensors around Hawaii so we can know where particulate matter is and know where it's going to be before it happens. So with this and with precision agriculture, we can look at the environment with a much higher resolution, and in this way we can learn exponentially more about the world around us. We'd like to thank
We would like to thank our professors. Ben Corker, Jesse Kroll, and Colette Heald, our professors. Josh Moss and Ben Crawford, our TAs. Richard Ha for letting us tramp through his cornfield and take some samples for days on end. MIT Civil and Environmental Engineering for sending us here every year, and all of you for coming to our talk. Thank you. Yes.
Do you know the predominant chemistry of the particulate?
Do you guys want to? That was your project.
Do you have the extra slide?
Yeah, so in general, we ranging from anything from dust, from pollens, but like in this case, we are focusing on the volcanic walk, right? So it's actually, we did have a slide
Yeah,
that
click
can
twice.
Explaining more about chemistry behind. So we have sulfur dioxide emitted from the volcano, and it would react with UV light or sunlight in general with oxide in the atmosphere, and create bisulfite and sulfite react again with oxygen, which equivalent in the air, and then the reaction go on and so forth, and then create the sulfuric acid, which is kind of sticky, so it stick together and then create particulate matter.
a model, and they plot maps of where the rock is going to be, and they seem to be pretty accurate just from empirical seeing. They publish them. It's a continuous website. Were you guys aware of that, and have you used that?
Yeah, actually we for the plume chasing part, we actually use that model and we go along the path of plume that is predicted on that particular day from National Park all the way to Kona. So this is the part that we got from that model. So
one of the things is that group that's doing it at the university has never published a calibration correlation. They got lots of they made lots of measurements, but there's no validity. So you guys could help with that. And so I'm thinking your instrument might be something that would be really helpful for the.
I think this is something they want to publicize.
There's a direct correlation with direction and intensity of breezes. And are you correlating wind direction and speed during your times of detecting the particulate matter?
we try to, but unfortunately the data from the Department of Health is in an hourly basis, so we did not have much data points that we can find regression on.
You could almost determine where the bog's going to be based on the direction of wind as well as the eddy currents that are flying. You can see the divider line almost straight up from Kylo to Kona. There's left is more boggy generally, and north is more clear. But then as the eddies shift more to from the south, they come more this way, or as you show on your map, or come from the north. I think that might be a variable that would be very significant in evaluating how much particulate matter is in the air in this particular area or any other area.
Do you want to go back to the chemistry slide? Did you do the same thing for phosphates?
Our sensors don't actually detect like what form of particulate matter it is. So we know the amount of particulate matter. We don't actually know what type of particulate matter. We assumed that we were generally following the volcanic plume just because that is the major source of particulate matter on the island.
So you don't have any data for phosphoric acid, that's it, right? You'll never have any data.
If you view more sensors in the future,
Next year, another reason to come back. So, do you guys need a reason next year? Because rapid ohia death and the coffee borer beetle are two localized problems that we're having, and using your drone over ohia groves and over the coffee farms to see distribution of how the borer beetle is.
Yeah.
That would be awesome.
Yeah, we focused on NDVI for our project, but drones have been used in a variety of agriculture practices, and one of them is monitoring using just images like every day or every week, just monitoring the spread of.
I was wondering if you can use the NDVI specific to the ohias or
I'm
to
sure
the
you
coffee.
could. Yeah.
You know, if you have a big coffee farm and you're seeing the distribution of the coffee borer beetle.
yeah, we
taking
actually
out
tested
swaths.
our drone. The first flight was over a coffee farm.
Oh, cool.
So yeah.
Nice dark leaves. They
Yeah.
give you good,
Yeah.
good register.
So will any of this research be continued? Are you going to leave sensors? Are you going to do anything, or are you done?
So all of it's going to be continued.
Okay.
This is, again, both of these projects were fairly early stage. So in regards to the sensors, we're actually leaving 6 behind on the island, and our TA, Ben Crawford, is actually going to be returning to the island and living here for a year and a half to continue the study.
Are we going to get a Massachusetts Community College extension here?
You sure gonna have it? I think so.
Oh, and then there's a follow-up class to this in the spring. So although we had to come to Hawaii, we're actually taking class.
Have to do something with it, huh?
Question. oftentimes in our computers in areas where there's airflow that's not really rapid, we see a buildup of fibrous particulate. Is that part of the sulfur mix? And do you know what that is? I mean, have you seen it? Let's put it that way. Like your airflow in your filter into the computer cage, you'll see a buildup of this fibrous material. And it's really it's sticky and it's almost humid to it.
Yeah, so I think it's outside the scope of 2.5 microns. So for our project, we weren't really focusing on that. However, I think there's a lot of validity in looking into that in the future.
Could be dust.
Yeah, I mean, primarily when I see that, I just think of it as like dirt in there, like dust. But that's just like an opinion. That's not actually like data or anything. So I think it maybe is like a side project as a result of this.
We have the added salt air to really stick it together too, which is nice.
Yes, I had a question. I asked this question of my son, the chemical engineer, and he laughed, but I will throw it out. Given global warming, given the envelope keeping the earth more warm, given the increase in volcanic activity, now, Kilauea not being the only one, is there any possibility that global warming is warming the planet enough to change the frequency of volcanic gaseous and lava eruptions? You don't have. You can laugh.
Well, unfortunately, that's just not what we studied, so we don't really. I mean, we can't answer that with any kind of, certifiable information because we don't know.
It's a lot.
Well, yeah, I mean, it's an interesting idea.
It's a hypothesis that could be explored, but we just didn't explore it.
Yeah, like, I mean, when you just look at average ecosystems with climate change, like at what point has the ecosystem changed and it's not just being affected? So I think it's something that in the future.
So we shouldn't call the paper and like put a quote from you guys stating
No.
right. MIT came here and said this.
I'm glad you can read through it.
Act now.
It's going to go AP. It's going to be all over the world.
Volcanoes will destroy the So if I were Mr. Ha, what might I take away from what you did? How would I do something different?
Well, the farmers are the experts in how to care for their crops, and they usually have intuitions about their crop areas, and because they've been doing it year after year, and they know their fields. And so what the NDVI does and what the precision agriculture work that we did is actually just give them more information at a higher resolution. And so the specific practices or care that he might decide to do, he can determine by all of the measurements that we got. And it's really up to the expert farmers to care for their crops.
We did ask him how he fertilized the fields, and he said they're pretty much fertilized all the same with nitrogen fertilizer, and I believe also phosphorus. So in that case, like, we would know in some areas it's not necessary to add nitrogen fertilizer, and in others maybe focus on that more. So that's definitely a major thing he could take away from that.
And then another thing to note is when we asked him how much is your soil tested, and he's like, they do it every once in a while, and they get a couple samples, one here, one there, and nothing really happens. But as you can see, we got 3 different types of data from a single flight, and that happened within 20 minutes. So this added precision and with the tool of the drone can give them so much information over the big field.
So you're going to sell them a drone?
There are actually a lot of companies that precision agriculture companies that will sell to farmers, and they have all cool types of drones and different equipment.
So is Richard going to buy one?
You gotta ask Richard.
Talk to Richard for it. Yes.
One last comment. Some of you may know that MIT competes athletically in Division III.
Yep. Except for crew, which I was on, which is Division 1.
Wait, time out. What about badminton? Are you guys have badminton
I
teams?
think it's club sport.
Because
Still, it's
Sorry,
very serious.
Go ahead.
I'd like to hear your football fight cheer.
Oh, do you guys know it? I know it. I know.
Oh,
First
no.
part.
This is recording, right?
If you want to hear the Philadelphia Eagles theme song, I can do it for you.
Go man.
Yeah. E to the U to U to the X, E to the X to the X. Cosine, secant, tangent, sine, 3.14159, integral, radical, mu dV, therefore, slipstick, spiral, MIT. Yeah! Woo! It's not just football. We sing it with the
They
creature
must
sings it before.
tremble with that. Huh.
They don't have Yale spike songs for the football team. Bulldog, bulldog, bow, wow, wow.
All right, this seems a good place to stop.
That was excellent.
I don't think we can come back.